Welcome to this presentation. My name is Vaibhav Pandey and I'm a graduate student at University of California, Irvine. And today I'll be presenting our work about personalized user modeling for context-aware lifestyle recommendations to improve sleep. So first, let's talk about why sleep is such an important problem and why we should try to improve everyone's sleep quality. Sleep is the natural repair mechanism for our body. It is essential for converting short-term memories to long-term, and studies have shown that a good night's sleep improves our learning abilities. Whether we are learning math, how to play the piano, or how to drive a car, sleep helps enhance our learning and problem-solving skills. Sleep also helps us pay attention, make decisions, and be creative. Sleep deficiency may lead to trouble making decisions, solving problems, controlling your emotions and behavior, and coping with change. Sleep deficiency has also been linked to depression, suicide, and risk-taking behavior. Sleep also plays an important role in our physical health. Ongoing sleep deficiency is linked to an increased risk of heart disease, kidney disease, high blood pressure, diabetes, and stroke. Even our immune system relies on sleep to stay healthy. For example, if you are sleep deficient, you may have trouble fighting common infections. And in these COVID days, ability to fight infection is very important. Lack of sleep can also make you less alert and affect your coordination, judgment, and reaction time while driving. Studies have shown that going too long without sleep can impair your ability to drive the same way as drinking too much alcohol. For such an important part of our lives, individual sleep is still not very well understood. The current gold standard for collecting data related to sleep is polysomnography. It requires the person to sleep in a controlled clinical environment with multiple sensors attached to their bodies. These sensors measure the person's physiological response, such as ECG, EEG, EMG, and respiration flow while they are sleeping. While the data provided by polysomnography is very accurate and multimodal, it cannot be replicated in a person's natural living environment due to all the sensors required. There are many consumer applications that allow individuals to monitor their sleep at home without investing into different sensors. These applications and devices typically use on-device accelerometer to obtain actigraphy-related features about the user's sleep, such as sleep latency and movements and awakenings while sleeping. Most of the wearable devices also capture the person's resting heart rate while they are sleeping. Some applications such as Sleep Cycle also utilize ambient noise to monitor a person's sleeping behavior and recognize sleeping events such as snoring. While these applications do provide useful insight in a person's sleeping behavior, they do not explain how other lifestyle events impact a person's sleep. What we do during the day definitely has an impact on how we sleep. Lifestyle habits such as diet, work, and exercise patterns and different environmental factors like temperature and humidity govern our sleeping habits to a large extent. While various scientific studies have explored these relationships in a controlled and experimental setting, those insights are valid at a population level and may not generalize very well for every individual. However, we can utilize the data generated by an individual to create a personalized model that captures these relationships for every individual. We live in an era of unprecedented data generation. Every day, an individual generates a large amount of multimodal data streams, and different applications and devices capture data about different aspects of our lives, such as sleeping, eating, or exercising. However, most of the data collected resides in individual silos and needs to be brought together to leverage it effectively. Once we have the aggregated life log, we can utilize cybernetic principles for recommending actions to the user that will take them closer to their predefined health goals. In this work, we have attempted to do this for optimizing sleep quality, but the same principles can be applied to other health goals such as managing diabetes or other chronic conditions. At the heart of the cybernetic loop is the personal model, which encodes how different events in a user's life are related to each other and how they impact the user's health state. We have used interval algebra and event mining to create a rule-based explainable model of the user's sleep that can be used to understand and predict sleep outcomes. We use an event pattern language derived from Allen's interval algebra to represent temporal relationships between the events. Every event pattern has at least two events that are related to each other through a temporal constraint. For example, pollution exposure is usually followed by difficulty breathing. High humidity events are frequently concurrent with sleep interruptions, and alcohol intake is usually followed by sleep interruptions in 3 to 4 hours. We can also use event operations to create new event streams from the existing ones. For example, we can create a new event stream called exercise that includes all the events from running, walking, cycling, and swimming event streams. Now, every event during a user's day has some impact on their health. This can be quantified by certain attributes of the events, such as for exercise, the attribute might be calories burned or exercise duration. Or we might want to find some sub-events during the lifestyle events, such as REM sleep or slow wave sleep during a sleep event. We call such events health interface events, as these are the events that are relevant to a user's health state. We utilize the event pattern language to specify patterns relating one or more interface events with sleep outcomes and search for those patterns in the user's event streams. The set of rules and behavioral patterns represent possible causal relationships that determine the person's behavior and biological outcomes and need to be tested while controlling for the confounding factors. We create different subsets of the input-outcome event pairs based on the values of the confounding factors and find the effect of the input event on the outcome within each subset. For example, in this case, the confounding factor is exercise levels during the day, and we create 3 different pairs or 3 different subsets of temperature event and sleep outcome event pairs, and within each subset we find out the impact that temperature while the person goes to bed has on their eventual sleep outcome. The verified rules are added to a rule-based personal model of the user and can be used to make predictions and provide recommendations in different contextual situations. We will talk more about making recommendations and matching context in the next slide. As we collect more observations about the user's sleeping behavior and daily activities, we need to keep updating the personal models with the latest data so that the personal model reflects the person's latest habits. As new events appear in the user's daily event log, we derive the interface events from different lifestyle events and add the relevant health parameters to the user's context. These contextual variables would need to be defined in advance and will depend on the types of events that are available in the user's life log. Thus, any new event that happens during the user's daily life can change the current health context, and we need to generate a new set of recommendations every time the user's context is updated. These contextual variables would need to be matched with confounding factors and the input event for different rules in the personal model. We choose the rule that matches the current contextual variables while maximizing the likelihood for the desired sleep outcome. For example, in this figure, after the dinner event, the user's context has information about their exercise levels during the day, stress levels, last night's sleep quality, and the time of meals for the day. The last variable, time of meal, was obtained once the dinner event is over. We match the available set of variables with all the rules and find that the closest match is rule B, as rule A does not match with the user's exercise levels for the day. The confounding factors and the intervention event that do not yet have a value, that is temperature, or whose values can be changed with a new event, such as stress, are considered as items that can be controlled and are generated as recommendations. These recommendations can be sent to an automated system such as HVAC system that controls aspects of the user's environment, or can be sent to the users themselves if it's an action that the user needs to take, such as meditating to lower their stress levels. We tested this system with data generated by a 31 years old male athlete. The data was collected using a smartphone using sleep cycle and Strava applications to collect sleep and exercise data respectively. The individual also used Garmin Phoenix 5 to collect data about their heart rate and their sleeping habits. And we also used a small IoT device called Sensor Push to collect data about the user's local environment, such as their room temperature and humidity. We applied the specified thresholds on different data streams that we collected to create different lifestyle and sleep events. For example, if the person had no exercise during the day, that day was labeled as none for the exercise minutes per day. if the user had between 0 to 50 minutes of exercise during the day, then that was labeled as a poor exercise event, and so on. Similar thresholds were also applied on different sleep outcomes, and different sleep events were labeled accordingly. In our experiments, we focused on two things. One was creating the personal sleep model for the user, and also describe the average effect that different lifestyle events have on different sleep outcomes. And we also created two sets of models to predict sleep outcomes in different contextual situations. One was a static model, which was created using about 70% of the data, and was tested on the remaining 30%. And the other was an online model that was continuously updated using daily sleep and lifestyle events. So the first step was to finding what are the confounding variables that had significant impact on a relationship between a lifestyle event and the sleep outcome. And this figure represents significant confounding variables for all pairs of input event and the sleep outcome variable. And we can see that the meal timing is a significant confounding variable for the relationship between exercise minutes during the day and sleep latency. And similarly, exercise minutes during the day were a significant confounding variable for the relationship between meal timings and sleep latency. Now, the next step is finding the effect of a lifestyle event on particular sleep outcomes in a specific confounding situation. We find the effect of lifestyle event uh, by comparing the conditional distribution of the outcome variable for one level of the lifestyle event, which we designate as the baseline level, and comparing that distribution with the distributions for the with the conditional distribution for the other levels of that event. For example, in this heat map, we compare the distribution of minutes awake during a sleep event for different levels of the input variable time, that is time spent between two sleep events. This event has three levels. One is greater than 17 hours, the other is between 15 and 17 hours, and less than 15 hours. And we find that uh, this particular variable or lifestyle event significantly impacts the sleep outcome, that is awake minutes during the sleep event. Now this slide shows the average effect that different input or lifestyle events have on different sleep outcomes. And we find the average effect of an input event by averaging the effect of the different contextual rules that are found to be statistically significant for that particular event. We can see that for this individual, increasing exercise duration leads to improvement in all sleep outcomes, while both high and low temperatures lead to a worse sleep latency as compared to average sleeping temperatures. Now, for predicting the sleep outcomes, we trained two sets of linear regression models in different and we wanted to compare the difference between the adaptive training strategy versus a static model. We plotted the RMSE errors for the two sets of models, and as expected, we found that the two models start at about the same error level, but the adaptive model is able to uh, uh, adapt to the user's changing habits, and its performance improves over time. For future work, we would like to incorporate further lifestyle events and data streams such as stress during the day and nutritional content of the user's meals. We would also want to integrate knowledge-driven rules that are derived from scientific literature and provide a user interface that's easy for experts in the specific domains to use. In our current implementation, the recommendation system is trying to optimize only a single sleep outcome at a time. While in a real world situation, you would have a user might want to optimize multiple health outcomes, such as they might want to improve their sleep outcomes while also trying to lose weight. And since we are matching the context with the possible rules in a greedy manner, uh, the current implementation will not be able to handle multiple objectives uh, accurately, and we need to spend more time and research into this problem. We would also want to create more sophisticated models for predicting sleep outcomes in different contextual situations. Thank you for listening to this presentation. Uh, Please contact me at my email ID if you want to collaborate or if you have more detailed questions about the work that we have done. And let's move on to the Q&A session now. Thank you so much.